Oh, I forgot to push the recording button. Just realized it. Oh my god. Okay. Sorry, Chris, but nevertheless, I guess you know everything about 1/2 0 and 0 1/2 representations. So I'm just starting with van der Waerden notation right now. What is phi? What is phi? Oh, I hope I'm ready for this. I actually read that part for, I don't know, 5 or 7 times already. Not sure, like, if I'm, how to say, like, kind of got used enough to that stuff. But I guess it's better than nothing. Overall, it kind of a generalization of the tensor indexes, but for spinors. We will see how it works soon. So it kind of help us to keep the track of how objects with different Lorentz representations are transforming, in what way. What's cool about that? What's cool about that is that, I guess, a basic stuff to get into Spinor calculus instead of working in a tensor calculus, and to disentangle every thing we have had before. I mean, like 4 vectors, like anything like V mu or something, or Faraday tensor or something like mu nu, F mu nu. In terms of spinors, so instead of these, you'll have something like A and B dot, and instead of that, you kind of could have something like A, B dot, C, D dot. Like it looks not so good in some sense, because like, you get in like more indices. You need to keep track of every index transformation there, which is a little bit more involved because you need to track the signs, chirality stuff, and like conjugation also with that dot. But what's interesting, like, is that it allows you to make the most simple object which transforms with the Lorentz transformation spinors to be in the like to be the main scene on a scene, right? The main actor. And in some sense, I guess that's why, not that's why, but like the reason why Penrose has written the book about Spinor calculus was that it gives you a new angle on a similar stuff you've seen before, and also in some sense it also simplifies a lot of formulas. So yeah, I guess like tapping on that can give you more insights, but it's harder. Like it's harder than working with vectors in some sense. But I guess Penrose believes that, for example, gravitation stuff is simpler. It becomes simpler in a Spinor notation. So, anyways, let's take a look on the like simple ways to represent spinors and how it looks like. So let's start with the left chiral spinor. So it's 1/2 0 representation, and in van der Waerden notation it just has the lower index, something like A here, and the right chiral spinor, it will have the upper dotted index. So that's like the basics of that notation. And now we have a spinor metric. I guess you already also seen that matrix. It's like small epsilon AB, and it has zeros on the diagonal and 1 and minus 1 off diagonal. So, and to transform, or like to get the conjugated spinor, what we need to do, we need to apply matrix to the complex conjugation. So that star operator just denotes complex conjugation, and he L, as we know, it's just like a complex vector. So in some sense, it's just also some AB, and right spinor is also some AB. So what's the difference between like up, lower indexes and the dot is just like the difference is in how that object will transform with Lorentz transformations. So because we know the transformations for the left and right spinors, now we know that these two objects on top, they look the same. They're just C2 vectors, but they do transform differently in terms of boosts. Yeah, but we also need that notion of the conjugation. I guess it's connected with getting from particles to antiparticles, as far as I remember. And you'll see it later. For now, just bear with me and just try to understand how it works mathematically only, like not on the physical base. So yeah, to conjugate the spinor, in this case, the left one, because for the right one, the formula will look a little bit different. It will have, I guess, the minus sign there. So we need to conjugate that vector complexly and apply matrix, Spinor matrix to it. And you can see that Spinor matrix, it has this relationship like minus epsilon multiplied with epsilon gives us the identity matrix. And also it has this relationship with polymatrices, where like a sandwiched conjugated polymatrix is actually equal to minus sigma I. So what happens here is that like we are asking a question how the conjugated spinor transforms, and we will just take a look at the results. I won't like get over all of these steps here. So what we have here, we have just our conjugated spinor formula. So it looks like it is, and we just put the transformation behavior here for the left Weyl Spinor under the boost. And at the end, we will come up with a formula which looks like this. So we can see that conjugated spinor transforms in the similar way, but it also obtains the minus sign. So what we've done here by conjugation, sorry, just I need to put a new minus here. So what we have done by the conjugation here, we actually transformed the left Weyl Spinor to the right one. So in this case, we see that the transformation behavior becomes the same as with of the right Weyl Spinor. I guess for the I don't know if he writes here, but I guess for rotations the transformation will be the same. It won't change. Yeah, let me see what is on the next page. Yeah, so here he just checks for the rotations, and that's true. So if we conjugate left Weyl Spinor, we just obtain in the same transformation under the rotations, so nothing changes. And that means that we kind of have a way to transform left Weyl Spinors to the right Weyl Spinors by using that conjugation procedure. And with left Weyl Spinor, we need to use minus e. So if you have like he, r, c, it will look something like minus e applied to he, r conjugated instead. And that's actually connected with the fact that minus epsilon equals to 1, or identity matrix, 1, 1 actually. Okay, so what Spinor matrix does actually, it actually put your indexes up or down. That's why we call it matrix. So in the same way, like Lorentzian matrix acts on vectors and just put up or down their indices, Spinor matrix in this case, it also puts your indices up or down. So that's all it does. Okay, but in the case if we will use complex conjugation here. Yeah, okay. So let me read a little bit what he says here. Yeah, I guess that like just putting up the index is not enough to get the right Weyl Spinor. So we have seen at the beginning here that right Weyls, they have top index with a dot, with a small dot added. And that's exactly what he's talking about here. So just adding a matrix is not enough because it will put your index up, but you won't get a dot. So to get a dot, you actually need to add complex conjugation. And that's exactly what the dot represents. So the Spinor conjugation consists of matrix and complex conjugation, and matrix puts your index up, and conjugation adds a dot to it. So that's how we convert between like he a lower to he a with a dot at the top. So it's the same as to say we convert between left and right chiral representations, or we also can say that we use conjugation, or like actually it will be called charge conjugation. I just want to say charge, but yeah, that C operation is actually like going from kind of like from particle to antiparticle, I guess. But anyways, okay, we will come to that later. I'm just rushing forward a little bit. So yeah, that operation actually brings up us from he A lower to he A at the top with a dot. And in a similar way, I guess, no, he just explains, I guess, here, like how the conjugation acts. So if you have conjugation on the right spinor or left spinor, we just remove the dot or add the dot, so it kind of just turn off and like switches the dot to like on or off state, basically. Okay, and now he says, like, let's take a look how he A with a dot lower and he A without the dot transform, because these objects are needed to construct terms from spinors which do not change under Lorentz transformations. And that's the case for the spinors. It's not enough just to know how left and right here chiral spinors transform. We actually need to know how their conjugated versions transform too. So we need to have a track of the 4 different versions of the Lorentz transformations, unfortunately. Here we see the actual way of the left chiral spinor transformation, how it's done. So we see the same exponentiated Lie algebra element here with phi and thetas, and we see that it has 2 spinor indices, in this case A and B, and this one has like just a lower index B, like left spinor should. And by knowing how to get to the like dotted versions, we actually can derive how the dotted version will transform. So we just apply here the complex conjugation, which is the same as to put a dot over the index. And to transform it, we need to transform first the left chiral spinor, well, I'm still swapping the names, the left chiral spinor, and apply the complex conjugation to it. So we put the same transformation we have had in the previous formula. We put the conjugation to the spinor itself here, and when conjugation comes down to the matrix, you see that it also acts on both indices here. So we are obtaining 2 dots in here, we are obtaining 1 dot here, and what we have here, like we have a complex conjugation falling through the exponential to the Pauli matrices here. And I guess that he should somehow transform these Pauli matrices, because we know that okay, I kind of got it. So like you see that he left, like he's leaving the thetas, sorry, sigmas here with a star. So he doesn't just complexly conjugate them. Why? And the answer is because he needs a transpose to apply here. Because for the sigmas, we should have sigma dagger equals to sigma. So the complex conjugation is not enough. One moment, sorry, I need to close the door. Yeah, so, and that's why he is waiting for a little bit to combine everything into a nice looking formula. So I guess he just derives the similar stuff, but for the right chiral spinor. So in this case, we know that right chiral spinors, they have top dotted index, and the transformations, they will also have 2 dotted indexes, because like right chiral spinor should transform to the right chiral spinor. And we have that minus sign applied, as you can see, for them, for the boosts. And after that, we just derive the similar equation, but now for the right chiral spinors, which are conjugated, so without the dots here. And we are obtaining really similar formula, but now you can see that the first, also only the first one term here was conjugated, but the second one, it obtained minus from the right chiral spinor behavior. Okay, so, and here you can see that he says that like, and I even put a note here about transposition of spinors. So to be able to write products of spinors that do not change under Lorentz transformations, we need the transposition. So it's kind of similar to the scalar product of the vectors. So scalar product is invariant and like over the matrix, because matrix kind of sets it up, right? And we kind of have a covector like A transposed producted or like multiplied with B vector. And in similar way, we should transpose one of the spinors and add another one to the product for the term to be invariant. And what he does here, let me take a look, like he says that For example, we can use this term like he a with a top index transposed combined with he a, and it won't change. Why? Let's take a look what will happen. Let's take a look. So if we combine two spinors, so it's like right conjugated spinor, right, transposed, plus left spinor, then the combination will be invariant, so we will be able to include it to our Lagrangians, and they won't change. Why? Because in this case, you see that we have that formula with the stars here, and plus transposition here, and now we can use that fact that sigma dagger equals sigma. So we just put the transposition one level down, closer to the stars, and because of that, we can just apply this formula, this one, and just get this, and you can see that now we are getting two minuses here, two pluses here. They cancel each other out, and what we come out, like what we have at the end, is just the same combination as it was before the transformation. So that's exactly why we are getting the invariant term while combining right conjugated and left non-conjugated spinor. And that's exactly the stuff which will be included to the Lagrangians, actually, like connected with the Dirac equation, for example, like talking about spin 1/2 fields. In the same way, we can combine an upper dotted index with the lower dotted index with a lower dotted index with a lower. Yeah, okay, yeah. So here he just says like if we forgot, if you had forgotten about the conjugation and just combined right chiral spinor with the left one, we won't have the minus sign here, and because of that, we won't have the identity matrix here, so we won't be able to get the invariants here. So therefore, we cannot just combine left chiral and right chiral spinors because the term won't be Lorentz invariant. And to conclude, we must always combine upper with a lower index of the same type in order to get Lorentz invariant terms. So that's the case, and that's why actually like Waerden notation is also like good one, because we can clearly see that like the right combination to combine will be something like this, or maybe something like, if you want to do like maybe something like this, so it will work. But other way around won't. And that's why we need to keep track of the 4 variants of the transformations. And I actually put them in here. It's a little bit encoded, just to make it a little bit, I don't know, compact. And the signs I have here, actually, you can see, let me try to explain. So R and L here corresponds to right chiral and left chiral spinors. So we can see the corresponding van der Waerden notation or spinor calculus notation here. So left spinors, they have lower undotted index, and right, they have top dotted index. And pluses and minuses are actually signs for the corresponding terms in the exponential here. So you can see that we just have, in every case, we just have the same exponentials, the same transformations, the rotations and boosts, and the only difference is in signs. And signs will just switch off kind of in a circle. So for the left chiral, we just have 2 plus signs there. For right, we have plus and minus. And now we can just conjugate. So during conjugation, we know that the only stuff which will change its sign is the stuff which has I in it. And in this case, it's only the rotations part. So that's why conjugated right chiral spinor, I put it like R minus here. It will transform so rotationally with a minus sign. So that plus goes to minus. And in a similar way, this plus will also go to minus when we conjugate the L minus spinor here. Yeah, so that's the basic idea, I guess. And I also have put the transpose here. So it's not just the conjugated spinor, it's actually a conjugated transpose. And why I have put the transpose there? So that's the same reason, not to include like that implicit star into the formulas. So I want to get rid of it. And to get rid of it, I need to use a transposition, as I know from the formulas here on the next page. So I'm kind of using transposed conjugated spinors because they kind of lock nicely with non-conjugated, non-transposed, like original variants with nothing added, right? So we just getting nice exponentials with no complex conjugation in the sigmas We just have sign switched and that's it. So yeah, if it's a lot to keep track of, so I guess like it's not, it's of course it's not compulsory to remember everything. You need just to catch the gist of the idea. You can always come back to these pages and refresh yourself. And actually that's what I'm doing time to time here. Yeah, and I also advise you to take any notes. It's really great to just to think on the paper, you know, to kind of, how to say, to give more, to get used with that stuff written in the book while writing. Okay, so yeah, at the bottom of the page here, he also says that, like, look, in the tensor calculus for vectors, we have formulas like that. And we know that if we have the bottom index, it already means transposed here. So, like, in some sense, we have, like, x vector transposed multiplied by the matrix here with y. So we have, like, 4 by 4 matrix, and here we have 1 by 4 row, and here we have, like, 4 by 1 vector, so everything kind of combines nicely and spits out the 4 by 1 vector. Sorry, not 4 by 1 vector, 1 by 1, so just a number, because it's a scalar product, of course. Okay, so why do we write the transposition for spinors? I actually don't remember exactly, but I guess it's really easy to forget about transposition with them, because of what? Because matrix just moves index lower, or like to bottom or to top, as you can see here. But with transposition, probably it's just like, maybe just not to forget about the right transformation behavior. I don't know, but I guess that's the main reason. I'm not sure why we're not putting transposition here also. Maybe we should put it. Not sure. Bradley said that he had to drop off the call. Oh, okay. Not a problem. Happens sometimes. Let me take a look at this note. Maybe that note will say something to us. Don't get confused why we have no transposition for the 4 vectors. These equations can be read in 2 ways. On the one hand, as vector equations, and on the other hand, as component equations. Okay, and it's conventional and sometimes confusing to use the same symbol for the 4 vector and its components. So it's kind of like components, like, okay. And if we read the equation of the component, we need no transposition. That's why it's not written. Okay, and the same is of course true for our Spinor products. But nevertheless, we have seen above that we mustn't forget to transpose. And in order to avoid error, so yeah, that's the reason we included the explicit superscript t. Also, the Spinor equation here can read in the same way as well as for the vectors. So yeah, just to track everything down and not to forget. It's better to include transposition to the Spinor calculus formulas. Okay, what we have here at the end. Okay, so he says like that we can also write the Spinor matrix with lowered indices now. Okay, and in addition, we can now write the 2 transformation operations as one object, some gamma. Okay, so just Lorentz transformation. And in this case, he just writes how the right and left Spinor transform. So it's the same. Actually, these are the same formulas we have seen in the previous section, but written with 2 spinorial indices, and that's kind of it, you know. So it covers up like 2 main cases with no conjugation and transposition. So kind of only the half of the cases, because you also need minus plus and minus minus case for the corresponding conjugated spinors. Yeah, and he said this notation is useful because, as we have seen, the 2 different objects aren't so different after all. In fact, we can transform them into each other, and unified notation is the logical result. Okay, but yeah, I guess it was just done to say that we can write something like gamma AB and gamma B dotted and A dotted here, so just to use them in the next section. Okay, do you have any questions for me? Was it confusing? How do you feel about that stuff?
It's cool.
Okay.
I'm a huge fan of the whole Lorentz Group representation thing. It really blew my mind when I first learned that the Lie algebra contains 2 copies of SU2. It's really cool.
Yeah. Have you learned it for the first time here or at the university?
No, last quarter in QFT.
Got it. Okay. Yeah.
Yeah.
It kind of surprises me that there is no quantum mechanics yet in some sense, and like you're getting spinors for free just from the representations of the space-time. It kind of blows my mind a little bit. Like it's a really interesting fact that like that's exactly the scene which is the simplest stuff transformed by Lorentz transformations. That's like very surprising.
Right. In other words, you could use spinors to describe ordinary, like classical rotations. It's just that there'd be some redundancy, and the phase factor doesn't really play a physical role, but you can still use it as an accurate description of rotations.
Yeah. Okay, one moment. I need to grab some water. Just have a dry throat. One moment. Need to drink something. Oh, nice.
While you're grabbing some water, I did want to ask a question. So this is the representations of the Lorentz Group, and I see we're using this like Minkowski metric everywhere. What about not Minkowski space, but like full on GR? Does it appear so naturally? And like, what happens to the metric?
Sorry, I missed the question.
Oh, that's okay. Is my signal all right?
Yeah, all right. Yeah.
Okay, so my question was, since it shows up so naturally here when we're talking about representations of the Lorentz Group, like you said, like you don't even need quantum mechanics. Well, I'm just curious, like how much this depends on the fact that it's like Minkowski space that we're working in, and like if you had a different metric, like I don't know, say Schwarzschild or something, like do the spinors pop up just so casually?
That's an interesting question. Like I don't know. Unfortunately I don't know yet. Yeah. I just cannot say anything about that stuff.
I see. I asked because we use the Minkowski metric all over in that van der Waerden notation.
But like, where the Schwarzschild matrix comes from? Like, it comes from the Einstein equations, right?
Yeah, like the Einstein field equations, the solutions to those are metrics, and I think you would use those metrics in place of the Minkowski metric. But I don't know if it's just direct substitution in here with all these same equations.
Like, I guess with general relativity, like we are having like a Lorentz-like manifold with a like it may be different matrix attached to every manifold tangent space. So yeah, I actually I don't know. Like I cannot answer that stuff right now. It's a hard question. Like the only thing I heard, that people talking about some like Betty numbers, I guess, and stuff. Remember that like there is some kind of a homology or some kind of a topology invariant which should be equal to 0, like second Betty or something class going to 0 for a manifold to have spinors on it. So I guess it's kind of connected with that question.
Okay, and maybe the answer involves twistors too.
Like twistors are connected with spinors somehow. Like I don't know yet how. But usually when someone says word twister to me, I imagine that like lights here, like when you turn on a flashlight and light travels at the spherical surfaces from you. It's or like you standing in between the two light cones, like past and future light cone. And I guess like Penrose was thinking a lot about the light while working with twistors, because like it's like everything connected with twistors is connected with projective geometry and light rays. But yeah, still cannot talk much about them. Like just seen some videos of Penrose and just grab that idea of the rays. But I'm not that deep. Don't know about the twistors yet to explain them. Nevertheless.
Well, that's interesting. I mean, thank you for exploring. I do have one more question on that, which is that it seems like these spinor indices like don't show up when you look at like the Standard Model Lagrangian and stuff. Like everything, it's like hidden. It's in there, but like people aren't explicitly using that, and I'm curious why.
They're all contracted, right? Like on the Dirac equation.
Yeah. We will see. Like we will see everything. Maybe I can even jump to something to show to you. Let me take a look. I guess I should have something saved in my bookmarks here about that stuff. Rotations, boost, maybe here, maybe no, maybe here. Probably that's it. Yeah, so like we will talk a little bit more about that stuff today, I hope. Like, why do we need Dirac Spinors? And the basic idea is that we need to have the parity transformation, and the parity transformation will turn your left spinors to the right spinors, and because of that stuff, is it parity? Yeah, it should be parity, I guess, in the text. Nevertheless, so we have that symmetry should be should be satisfied, and because of that we need like two spinors altogether. So to describe any particle we need both like the left chiral and right chiral spinors. One moment, I will close the door. Too many doors here. Okay. And because of that you can see the two spinor indices, they are hidden in the Dirac spinor, and like I guess that's what pissed off Penrose a little bit, you know, in terms of using Dirac spinors. I mean, if you have like Dirac spinor, usually it's like something like A, B, C, D, and you cannot see at all that you have kind of like two spinors here, right? You just have like a 4 vector, and you like confused a lot, especially as a student. Like, why do I have 4 vectors there? Like, what does it mean? And actually, like, the one at the bottom is the right-handed spinor, and this one is a left-handed spinor. They have different transformational behavior and stuff. And also, like, to combine them in a nice way, that's exactly what we have talked about. You need to combine them complexly conjugated and transposed, or it's the same as to say daggered here. And it means it's the same as to have left spinor daggered with combined with right, or right daggered combined with left. And let me see, like we will talk about vectors soon, so you will understand better why for the 4 vectors we have these 2 indices. And in the same way for the derivative, we have the same 2 indices here. And actually, like because 4 vectors, they have that form, that's actually, like this formula here could also be understood from the way you can understand SL2C Lie algebra. So SL2C Lie algebra, it's formed by 2 by 2 matrices. And these 2 by 2 matrices are in 1-to-1 correspondence with 4 vectors. And the generators of it are actually our Pauli matrices, sigma i's, plus identity matrix. And that's exactly what we have here. So we have 2 spinor indices for the Pauli matrices here, and 1 vector index here. So it's a combination of tensor and spinor calculus. So we just multiply the 4 vector components with sigma I matrices. And from mathematical perspective, it's just an SL2C element. So just reconvertation of the 4 vector to the 2 by 2 matrix, and just another representation which is equal and isomorphic. So it doesn't matter which one you will use. So you can understand that in that way. And in the same way, you can obtain the operator, spinorial operator in this case, by applying the same convertation procedure for the gradient, like derivatives, right, for the vector of the derivatives. So you obtain a matrix representing the derivative. And with all of that stuff applied, you can actually get more Lorentz invariant terms to include in your Lagrangians with spinors. So, and you can see that you contain in the same way a conjugated transposed spinor on the left and the regular spinor on the right. So the left one here on the right. And what we have here is just I guess it's just the same formula as here. So we just have a derivative encoded as a matrix for spinors. We can also have written it like it's written above, like DAB dot. And usually people don't use these. They, I guess, will usually use something like that, right? So they just write like left chiral spinor with dagger here, and just d mu combined with the vector of the Pauli matrices in here. So something like that. And it's in the same way we can obtain similar stuff for the right chiral spinors here. And at the end, let me take a look to the next page. Yeah, so that's what's happening. Oh my god, okay. So they just introducing Dirac matrices here. And let me see what I have highlighted here. Don't let yourself get confused why d mu acts only on one spinor. We are going to use these invariants and Lagrangians, which we always evaluate inside integrals, and therefore we can always integrate by parts to get the other possibility. Okay, yeah, so like that's the question about like the generality of these terms, like why we are using only term where we have derivative acting only on he left in this case, and not on the he left dagger. And the case is that this integration by parts, we can switch in between these two terms and kind of include the other one to the Lagrangian automatically after that integration is happening. So it's that, therefore, because of the integration by parts, which kind of just another form for the derivative of the product, something like AB derivative equals A derivative B plus B derivative A, but for the integral calculus, it will be something like integral of A derivative B dx will be AB minus integral of B derivative A. So it's the same line of reasoning why we are not using another terms with derivative applied to the daggers. Nevertheless, okay, that was just a remark. Now you can see how everything kind of, how the encodement or like encoding is applied. So we are getting further and further into the Dirac Spinors and like adding more layers of the encoding. So as we have talked before, we need both. We need left and right chiral spinors to represent the fermion, our particle. And because of that, we need to introduce these matrices. And in some way, it's kind of natural. It's more natural, I guess, to see how Dirac matrices will arise, because all of them, they will have a form, like a block of diagonal form, with sigma matrices and sigma conjugated matrices correspondingly, depending on the index of the Dirac matrix. Like if it's on top, we have conjugation here. If it's on bottom, we have conjugation here, blah, blah, blah. And it's totally connected with the stuff of, like with the fact that Dirac Spinor is actually some kind of Hiel and how it's really written, like some sigma R, like combination of two spinors, left and right. And if you put into account the formulas, the invariant terms we can get from the formulas, then we can notice that we can use these Dirac matrices to encode all of these invariants. So for the first two invariants, we can actually use this form where you have Dirac Spinor daggered combined with gamma 0 and another Dirac Spinor. So we just have these, and our sigma 0 here applied. But sigma 0 is actually identity matrix, so it doesn't matter like if we just omit here. So we just get in the same stuff we were talking about in the chapter 3 just a few minutes ago. We have a conjugated transposed spinor on the left and the regular one on the right. Combine all together, they transform invariantly via the Lorentz transformations, and that's what we are getting with that term. And also there is another term which combines now the same stuff, but you can see we have Dirac matrices applied to the d mu here. So it's the same way, it's a really clever way, but how to encode like two spinors at once. Sorry, no, it's not even just two spinors, but the two matrices acting on two spinors at once, actually. So in this case, it's kind of the same as having a gradient vector and trying to encode it with two SL2C elements, the same way we have done in the previous block, but now we will have like two 2x2 matrices instead. So, and that's why Dirac matrices have also those two blocks, because they will correspond to the different spinors transformations. So, and exactly in the same way, so we just combining our d mu with the sigma matrices to obtain 4-vector to the 2x2 matrix conversion factor. Why do we have this here? I guess it's just a convention, or yeah, because it's just a unit matrix. Like it won't apply. We can remove or add this here, but I guess it's just a convention here. And it will give us the other two invariants. And yeah, nevertheless, sorry, I'm not right here. I should remove it. Like it's true that sigma 0 won't impact spinors, but I guess like a 4x4 matrix, probably it will impact and mix some components here. So like on the right here, yeah, you can remove them. It's okay to remove them on the right, but probably it's not okay to remove them on the left. You need to apply them, right, to be applied to the different like parts of the Dirac spinor, to the Weyl spinors. So that's exactly what's happening here. We just apply like a derivative operators in the matrix form to these and these spinors. And we are combining, also adding like those gamma 0 and gamma 0 conjugated. You can see that sigma 0 is just the unit matrix, and we have conjugation equals to of the unit matrix equals to the unit matrix here. So if we just remove these, you can notice that it's the same form we have had on the previous page here. So these terms are exactly the same, and they will be also invariant over the Lorentz transformations. Why? It's a nice question. Why? Maybe he has said something about that here. Okay, maybe we'll concentrate about that stuff later. Nevertheless, I guess, yeah, I'm not sure why, but probably if you will write everything down, like, then everything will cancel out. I mean, because the derivative matrix will be having like two Spinor indices. Probably one index will catch the transformation which will cancel out with the left Weyl Spinor, and another will cancel out with the conjugated one. And it's a natural thing to have like there. I guess that's the reason why, but probably he haven't written everything in there. Okay, so that's exactly the encoding. And I guess that Joe and Darius, maybe Alex too, at least like, I mean, in the university or maybe somewhere else, I bet you probably have seen more of this than something else, right? Like Dirac encoding.
Yeah.
But people, I guess, usually do not talk much about Weyl encoding and Spinors.
About what kind of Spinors?
Weyl, or Weyl.
Weyl Spinors?
Weyl, yeah.
Yeah, they came up in Mickey in his textbook,
yeah.
And then we start with Weyl and then show how you can turn them into Dirac Spinors.
I just guess like that, like Dirac representation in this case, like if you do not understand nicely the constituents and the parts of it, it can ruin your understanding, you know, because Dirac notation is already having a few layers on it on the top, and it's really confusing, like to see 4 vectors which are not really the 4 vectors, and 4x4 matrices which are really not the like regular 4x4 matrices, like they're actually like 2 index spinorial objects.
Right. Yeah, that's the thing, is that the Dirac Spinors are not 4 vectors. And yeah, in some sense,
yeah. So
right.
So we can say that they are actually this representation, right? So 1/2 0 plus 0 1/2. That's exactly what Chris been telling to us in the last call, and that's what's happening.
Right.
Like I guess that's why like representation theory discourse, which was happening on our calls for the last year, I believe, like it kind of clears it up nicely.
Yeah, and I think that in some sense the reason we do that is to get it in a form that we can have it be connected to vector representations, right? By adding the 2 Spinor representations together. Which is not to say that the Dirac Spinor is a 4 vector. It's not, but I mean, for instance, the gamma matrices carry 2 Spinor indices to contract with the Dirac Spinors, and they carry also a Lorentz 4 vector index. So they can talk to both in some sense.
Well, to your point about making it work with vectors, it's historically, I mean, that's how they got QED to work, right? And the way they teach quantum field theory is somewhat historical now, like, and they start with QED. But when you get to like talking about the electroweak unification, and in particular the Higgs mechanism, they do start to talk in the Weyl representation again.
Yeah, I hope we'll talk about that stuff also soon, maybe in a few calls. But you can see that usually we also contract or like put gamma 0 into the dagger and just write like that gamma with like conjugation bar over the top there. And by using that, we can also like just obtain nicely looking formulas like that. So that's the form of the Lagrangian density, which is possible in this case. So we just have like psi bar, psi with some constant, and similar stuff like psi bar, gamma mu, d mu, psi with another constant. And like if you try to understand like what are these constants, I guess he just putting them there. So he just puts like mass and minus, an I. So we are actually having the right Lagrangian to obtain the Dirac equations after we apply Euler-Lagrange equation, right? So like I guess we could have done it other way, right? Like we could have applied Euler-Lagrange equation, then deduce what constant should we have to obtain Dirac equation. So it's kind of a little bit of the hacking, but it's great stuff. I mean that by including the simplest terms which are invariant, we are automatically getting the Dirac equation here from the variational principles. So yeah, it's a little bit like we do not see any kind of we do not see Spinor indices right away here, right? We just see Dirac, and we see vector indices here applied in Dirac matrices, but everything is there. It just lays at the bottom a little bit. Okay, I hope we have 5 more minutes at least, so I can just finish up with the vectors quickly and the vector representation. I guess it won't be long, and we will stop today at it. And next time we will talk about Spinors and parity transformation, Spinors and charge conjugation, infinite dimensional reps, and Poincare group. So I guess that's the plan for the next time. Okay, so the next representation is called 1/2 and 1/2. And in this case, we won't have n plus or n minus equals to 0 now. So both of them will act as Pauli matrices in this case. Sorry. What he was saying here, he's saying that instead of examining, like if we have a 4 vector, let's think about how we can represent it by using the Spinor indices. So like, can we encode the 4 vector with 2 by 2 matrices? And he says we also, instead of examining A and B in index being on the top, we'll just put it at the bottom. But we can, of course, get from one to another just by using the right Spinor matrix with the dotted indexes here. Nevertheless, like he just shows us the formula to convert in between them, and actually, as I have already said, behind that formula lies the correspondence between 4D vectors and SL to C, the algebra. So we have SL to C, the algebra basis here, Pauli matrices and identity matrix, and that's exactly how we can convert between 4 vectors and corresponding like spinorial or 2 by 2 matrix representations, and he just declares right away that it will correspond to AB dotted bottom indices here. He also shows the formulas to convert here, like how to go from one rep to another, like just put the index to the top. Probably it would be nice, like we don't have time today, but maybe it would be nice to write out something explicitly, calculate that matrix with dots also, and take a look how everything will change. But overall, I guess it will be like isomorphic up to the sign. So in general, you'll have something like that. You can see that time coordinate will combine with z here, and x and y will have the corresponding like complex combinations of diagonal terms. He also says that it's really just a basis choice. Like you can, of course, can choose another basis, but I guess Pauli matrices are kind of natural, something like that. Maybe it will be useful for the applications. I don't know. Can't say right now. Okay, so that's how we convert like 4 vector to the 2 by 2 matrix, and can use it with the Spinors. And in Spinor calculus, you can see that how that object will transform, right? We can ask the question. And one moment, I need to plug in my charger, not to let my Mac die out. Yeah, I'm back. So you can see here that one index requires one spinorial transformation. Here you can see 1/2 on the left and 1/2 on the right, and we just attaching the corresponding indices here. You can see that we have also like stars and transposed here. We have the indices which are dotted, so we have D dotted attached to that D, and C attached to that top C here. And if we will apply everything, you can notice that what happens here, we just apply sigma dagger equals sigma, and we are obtaining formula like that, where the only difference you have is that sign, because it was conjugated, I guess. Okay. He now checks that like all of these matrices, they will be Hermitian matrices because they are in the SL to C algebra, I guess. And so he just checks that 4 vector under such transformation will be conserved in terms of like it will be still the 4 vector in this case. So I guess that's what's happening here. Let me take a look what happens. So these formulas are the same, and then he uses this equation and just switches. He just conjugate here, like applies dagger to see that we will still obtain the same stuff here. Okay. What happens next? He just shows like one explicit example. Like let's imagine that we are boosting our vector v along the z-axis. What will happen to that spinorial object? So we just using the formula from the top, thetas are gone, and we just have phi here and sigma 3. We have the same formulas here and here, and after multiplication we obtain that. Okay, so he just now wants to probably calculate the exponential here. So here writes the formulas using cosines and sines hyperbolic. Okay, oh sorry. Let me take a look at the next page. I don't remember what will happen next. I guess he will just derive the formula which will transform everything using the hyperbolic sines and cosines. Yeah, so now he just converts back actually to the 4 vectors. Probably Spinor calculus in this case, in that case, is not that enlightening. So he just like tries to understand how the transformation will work, and we can actually see that it works exactly the same as boosts acting on the 4 vectors. So we'll obtain the same stuff, like his hyperbolic sines and cosines applied to the v0 and v3 in this case, because the boost was done along the z-axis. So that's why you have multiplication, but that exponential attached to v0 and v3 elements. It will be interesting to see what will happen if we will boost along the v1, like the x-axis. Anyways, we also don't have time for that today. Yeah, so that's just a few last paragraphs. What is here? So yeah, he just says that what we have shown here is that 1/2 and 1/2 representation in terms of spinors is the same as the vector representation. So the objects we are obtaining are 4 vectors. And we have seen now that familiar 4 vector is related to the more fundamental spinors. And 4 vector is actually a rank 2 spinor because it has 2 spinor indices. And it transforms using that 1/2 and 1/2 representation. Okay, and we can now see that 4 vectors are not appropriate to describe every physical system on a fundamental level because they are not fundamental. Because like we can have like a simpler objects, but we cannot yet split, right? We cannot yet just take the 4 vector and split it in the 2 spinors. But we can say that it is a rank 2 spinor having like 2 indices. That's the case, something like VAB. And that's the answer Jacob gives us to the question why spinors are the square roots of vectors. So it's the same way as vectors are the square root of rank 2 tensors. It's the same way to say, at least he thinks so. So I guess that's his personal answer in this case. So in the same way we could have had like some matrix MAB, and it's kind of like a product of 2 vectors, but it isn't because it's like a tensor product, right? Something like that, like VMW. But anyways, okay. So, and a rank 2 tensor has 2 vector indices, and the vector has 2 spinor indices. So it's kind of the same stuff. You cannot just like separate matrix into the 2 vectors. And in the same way, you cannot just separate vector into the 2 spinors, some, I know, high and could be eta, for example. But they have 2 spinorial and 2 tensorial indices. So to have 2 tensor indices, it kind of means that we have a representation on the vector space like VV. But what? 5 minutes. So yeah, so for the matrix we kind of have like VV representation, something like that. But for the vectors we have something similar, but with spinorial like spaces. In this case, it's kind of like C2 by C2, I guess. And we have basic building blocks as like SU2 reps, actually, like some kind of SU2 reps. Okay, so when we started out our studies of the Lorentz Group, I just want to read the last paragraph. Note that it consists of 4 components, and these components are connected by the parity and the time reversal operator. That's true. So actually what we were speaking about here was only about proper orthochronous part of the Lorentz Group. So that's only, I guess, that L plus with a arrow up. But we also have 3 not connected parts of O13 group, and they are connected by parity, time reversal, and PT, I guess. It's like conjugation, charge conjugation transformations. And therefore, to be able to describe all transformations, we need to find the parity and time reversal transformations, basically to move in between these disconnected parts of the Lorentz group. And that's what we will do on the next call. We'll talk more about parity and time reversal and charge conjugation and how they are connected with spinors and traps. Yeah, that's it for today. Any questions, maybe, or commentaries?
Well, I'll just say thank you, Slava. This was a good presentation. I'm probably going to rewatch the recording just so that I get all the little insights in there, because I do want to follow closely exactly all those transformation rules. It seems like, just for a little comment, the way that we represent these 4 vectors, that seems like what Chris had shown us before. He called it like a Pauli vector, where you like use the Pauli matrices as a basis. Mm-hmm. That was interesting to see.
Yeah. So like, I don't remember exactly in what context Chris been using these Pauli vectors, but like from my experience, they always are popping up while you're working with like SU2 Lie algebra, and then also its complexification. So like for SU2 Lie algebra, you only have Pauli matrices without the identity one. And only after the complexification, so if you will go to SL2C Lie algebra, you will obtain the 4 vectors. So you kind of can encode 3D vectors by using SU2 Lie algebra. And I guess it's connected with SO3, right? So it's the whole story repeated, but instead of SO3 and just rotations, like for SO3, we would have like SO3 rotations for the objects in the space and 3 spatial dimensions. And we are moving to its double cover, to SU2, and taking a look at the infinitesimal transforms. And we are getting like three Pauli matrices. And now, like if you will ask, like how to represent what is the most natural space, basically, to represent these rotations. And the most natural space in the Lie theory context is actually its Lie algebra, because Lie algebra is the vector space. So we are coming naturally to the scene which is called adjoint rep. Sorry. So we have like adjoint representation. And that adjoint representation means that we are using our Lie algebra as the representation space for the group itself. So we're kind of acting with that group on that stuff. And I'm just thinking that I guess that's where all of that stuff comes from. So like we have, we have kind of our rotations. So we have rotations here, and we have our Pauli matrices here. So all our like sigma I, where I from 1 to 3, live in SU2 Lie algebra. And that's why we can naturally represent vectors. Like we also can have SU2 represented on R3 in the same way. And that's how we kind of connect. We can prove that they are isomorphic. And we can use SU2 Lie algebra as well as R3 to represent objects on which rotations act. And it means that like our 3D vectors, they are kind of the same as Pauli vectors, as matrices. And the same story repeats itself with Lorentz transformations. But instead of SU2, we actually having something like SO13 plus with that arrow, something like that, like proper orthochronous stuff going on. And instead of another things, we have SL2C here, SL2C, and we have 4 Pauli matrices. But we have the same story about another representation being a representation on like R4, for example. And we just connect them. So yeah.
That's interesting. One more thing. It seems like the way that we're putting this all together, like we're tending towards writing terms that show up like when we write out the interactions of the standard model. but we're like doing it in terms of I don't know how best to say this, but like what's more fundamental to space-time, right? Like we're writing terms of particle interactions in a framing that's more natural to space-time, and that's kind of interesting to me.
Yeah, but do you mean that stuff we have seen about spin 1/2 Lagrangian terms? Yeah, or
yeah, exactly. Like the way that we're moving with this representation theory stuff is that we're finding ways to like take the terms that we use in particle interactions, but represent them in the most natural way for putting them in space-time.
Yeah, but I mean, I kind of translate what you are saying in my head, like that we are trying to like take a look at the basic building blocks, like irreps in this case, right? And we try to combine them in the way that they are Lorentz invariant. And like multiplication, it's kind of like an interaction, right? So you are talking about interactions, but for me, like it means just obtaining the Lorentz invariant term, which is a product of a few like spinors, for example, like a few reps, right?
Right. That is a funny difference in intuition there. But I mean, you know, every one of those Lorentz invariant terms represents a process.
Yes, of course. Yeah.
Thanks for mentioning the adjoint representation, because that's been something I've been trying to understand lately. In QFT3, we're studying like non-abelian gauge theories right now, and so we're doing like Yang-Mills theory, and we had to go really deep into group representations, and the adjoint representation is something I'm only slowly starting to understand, like the significance of.
Yeah, like in some sense, adjoint representation is one of the how to say, like it's not the simplest, but it's like the most natural way to get something fancy, like. But still, it's like natural, because like the only vector space associated to the Lie group is its Lie algebra. So it's natural to take it and try to model the group on its tangent space.
Yeah. Well, what's funny is that there's a representation literally called the fundamental representation, which is where the dimension of the for instance, for SUN, the representation that is which is n by n dimensional, is called the fundamental representation.
Yeah. So
but the adjoint representation, which would then be n squared minus 1 by n squared minus 1 dimensional.
For SU2, it should be something like C2, right? Like it's like to have two-dimensional complex vectors. It means like to have a fundamental rep.
Yeah, the fundamental rep of SU2 would have, you know, the generator matrices would be 2 by 2. So the Pauli matrices are the fundamental representation. But of course, there's n squared minus 1 generators, so there's 3 generators. So the adjoint representation will be 3 by 3.
Yeah. I actually was a little bit implicit here at this moment, because like R3 rep is actually connected with SO3 more, right? So it's fundamental for SO3, but you can kind of include SU2 to SO3. You can map it as the universal cover, like 2 to 1, and have SU2 representation on R3 also naturally by inclusion to SO3. So yeah, anyways. And what's interesting actually is that in Yang-Mills theories, you will have bosons, and every boson is the element of adjoint representation, as we actually talked on the bias calls about that GUTS paper.
And in some sense, that makes sense, because each of the n squared minus 1 generators represents a gauge field. So the gauge fields have to live in the adjoint representation.
Could you please repeat your statement once more? Just.
So there's, for SUN, right, the Yang-Mills theory, there will be n squared minus 1 generators. Like for instance, you know, SU3 will have 8, right? Each one of those generators corresponds to a gauge boson, which, so in this case, it's the 8 different gluons.
But it will work only, like you will have n squared minus 1 generators in adjoint rep. You need to see.
No, you will have n squared minus 1 generators in any representation. But the representation will tell you.
No, that's not true. That's not true, I guess. Or that's true. Let me think about it. I mean, if you have, I just know that adjoint representation for SU3, if you talk about that stuff, it is 8-dimensional. But of course, like fundamental representation. Okay. So maybe you have the same number of generators, but dimensions are different.
The dimension of the generators can be different depending on your representation.
Yeah. That's the part I was.
So the key thing about the adjoint representation is that the dimension of the representation is the number of generators.
Yeah, exactly. Right. Okay. Yeah.
So the gauge fields in some sense, or your matrix of gauge fields, put it that way, must live in the adjoint representation because you need to capture all n squared minus 1 gauge fields together into some matrix, so there has to be that number.
You know, I guess like my intuition here was also like a little bit other way around, because like what are bosons? They are vector fields, and because bosons they are vector fields, it means that they should be like spin 1 reps, right? And because of that, they are vectors, and because they are vectors, we can kind of do the same stuff we have done before. We can combine vector components like v mu, for example, with sigma mu AB. So it's the same stuff, and that's why they are at the adjoint representation, because they are vectors. Like bosons are vectors, like maybe it's another way around or other way around, but because they are vectors, we can re-encode them using adjoint representations. And adjoint representations are used because, maybe because, but I have the theory right now in mind, they are used because they are a natural tool to use spinorial calculus all the way down. So, like...
Well, yeah. I think the other key thing to keep in mind is like adjoint representation of which group, right? We need to keep in mind that like there's the Lorentz or Poincare group, which you've been talking about, but then in the context of Yang-Mills, in addition, there's the SU3 gauge symmetry, right? So that they're in the adjoint representation of that gauge symmetry because that there are 8 generators of that, in addition to being in representations of the Lorentz group. So you will have 2 different representations going on.
Yeah. I'm just thinking about like how to combine 8 Gell-Mann or Gell-Mann matrices with vector components. Like it's not that natural, right? Like for the Pauli matrices and 4 vectors, it seems really natural, like to do that stuff. But for 8 Gell-Mann matrices with some t indices here, like I'm not even sure if they will have just 2. Probably no, because they should be like 3. They should probably have 3 indices or something like that. I'm not sure, like some 3 indices instead of just 2, because they will be 3-dimensional, right? They are 3 by 3, I guess, right?
In the fundamental representation, they are 3 by 3. Yeah.
Okay.
But what you do for the gauge fields is that for instance, you can write a mu equals a mu with a superscript a, which is the adjoint index, times ta, which is your generator. And so you basically contract your 8 different gauge fields, each having a Lorentz index mu, with all 8 of your generators. So in that way, you create your matrix of gauge fields, which has both the Lorentz index, showing it's under the vector representation of the Lorentz group, and it has an adjoint index showing it's also under a representation of the adjoint representation of the SE3 gauge field of gauge group.
So yeah, I just was looking for that page with Gell-Mann matrices. But yeah, I guess we will draw some parallels later while taking a look at the gauge theory and stuff. Yeah, and how adjoint stuff is happening in there. What kind of symmetries? I guess we'll put something on in terms of parallels in between everything.
Cool. Yeah. Thanks.
All right, guys. Well, I got to drop off. It's been a very interesting conversation. Thanks again, Slava, for presenting.
Yeah. Thank you. Thank you. See you next week, then. Yeah.
See you.
See you. Bye-bye. Thanks.
Take care, guys.